you. Now, perfect. Looks good.
Okay. All right, thank you. Before starting, I would like to thank the organizers for inviting me to give this talk at this workshop and for allowing me to present my talk remotely. I'm Laura Venuti. I am a research scientist at the SETI Institute in California. And in this talk, I will discuss what we can learn about the physics of young stellar objects by combining multi-wavelength information and time domain information, and what are the outstanding questions in the field that Rubin LSST will help us answer or address over the next decade. So let me start with a definition. So when I talk about a young stellar object in this talk, I refer to a specific the stage of the star formation and primitive sequence evolution, where the forming star has already emerged from the embedded phase, so it's visible in the optical, and is surrounded by a disk of gas and dust that acts as a mass reservoir both for the central star and for any planetary bodies that may be forming within the disk. So in terms of ages, I'm considering an age range between 1 and 10 million years, which is the age range of interest for the lifetimes of protoplanetary disks. This cartoon shows a sketch of the main characteristics of a circumstellar disk around a young star. So the disk can extend out to a distance of about 100 astronomical units from the central object, and is composed of gas and dust in about a 100 to 1 ratio. The disk has a temperature gradient, so the outermost disk regions have a temperature of just a few tenths of Kelvin, and the temperature increases up to 1500 Kelvin or so in the inner disk regions as a result of the irradiation from the central star. And this means that at a distance of about a fraction of a tenth of an astronomical unit from the star, the temperature is simply too high to allow dust to survive in non-sublimated form, so the inner disk is composed only of gas. And if you move inwards, you'll see that there is a cavity that extends between the stellar surface and the inner disk edge. And this is because the young star hosts a very strong magnetic field, typically with a surface strength of a few kilogauss, which will truncate the inner disk at a distance of a few stellar radii from the star. And this means that the star and the disk are connected and interact via the stellar magnetosphere. And the main process that governs this interaction between the star and the disk is what we call magnetospheric accretion. So material is lifted from the inner disk plane and is channeled in accretion columns along the magnetic field lines until they impact the star at near free fall velocities close to the base of the accretion columns. So this impact produces an accretion shock, which is much hotter than the stellar photosphere, the temperature of about 10,000 Kelvin or so. And so this will emit predominantly at short wavelengths in the UV. So if we combine UV observations of the star disk system with optical observations that help us trace the photospheric properties of the star, and then infrared observations that allow us to trace the thermal emission from warm dust in the inner disk regions, then we are able to reconstruct the emission spectrum of the star disk system, and you can use the information to classify the evolutionary stage of the star and determine its fundamental properties. We can then monitor how these emission features change as a function of time in order to study the dynamics of star disk interaction. And we repeat the observations for large samples of stars in clusters of different ages in order to study the statistical evolution of these processes. So this is a more detailed view of what I just described in words. So this is the synthetic spectral energy distribution, or SED, of a young star that is undergoing a mass accretion from a thick disk that surrounds a central object. So here, the overall SED that we expect to observe from the star disk system is shown as a black solid line. And you can see that there are multiple components underneath that add up to form this overall SED profile. So we have a component that is driven by the stellar photospheric emission that is shown here as a dashed line. Then there is an excess emission at short wavelengths that is driven by the accretion shock. And then we have an excess emission across the infrared regime that is driven by thermal emission from the dust within the disk at different locations across the entire radial extent of the disk. So if we take the SED and we slice it into different filters, then we can combine these selective flux measurements to derive the color indices of young stars and their disks. and then use the colors to classify the evolutionary stage of the star and determine its defining fundamental properties and accretion properties. And just as a reference, I'm showing here two photometric systems and highlighting where these photometric systems, so these filters, would fall on the SED for a young star. So the first system is what Reco already showed in his talk yesterday. This is the photometric system that will be used for Rubin LSST. And in particular, I'm highlighting the U, G, R, and I filters. And then we have the two mass near-infrared J, H, and K filter. And if you look at where these filters fall on the SED, you'll see that the radar filters, such as R and I, that will be used with LSST, are mostly sensitive to the photospheric properties of the star. So they will allow us to trace the intrinsic properties of the star itself. If we add information in the U band, then we are able to probe the excess emission driven by the accretion shock. And so we can use the U band to distinguish between a young star that is undergoing accretion from a thick disk from a more evolved young star where accretion has already stopped and where the disk has largely disappeared. And then if we move out to the infrared, we can study the evolutionary stage of the disk itself. And this is what we can learn about young stars by studying the emission properties across the wavelength domain. But another important component to study the physics of young stars is going to the time domain. And this is because young stars are intrinsically variable on pretty much any time scale from hours to decades or longer. And this is summarized in this plot shown here on the right, where we have a collection of different physical phenomena and processes that will contribute to the overall variability profile that you observe for a young star over different time scales. And each of these processes would contribute a different amount of variability. And the main concept that I want to highlight here is that LSST, thanks to its design, so the wide fast tip coverage over a baseline of 10 years, will allow us to probe a significant fraction of this entire timescale domain, like from weeks to a decade. And you see that there is a color code for the processes that are shown here on this diagram. And different colors correspond to different sources for the variability. So for instance, the processes shown here in gold correspond to variability driven by the magnetic activity of the star, such as star spot modulation or flares. And these processes typically correspond to a baseline variability level of young stars, above which we have more substantial variability that is driven by the accretion dynamics, shown here in blue, that leads to a different distribution of accretion shocks at the stellar surface that can change depending on the accretion efficiency. And then in red, we have the variability driven by the specific star disk geometry, so the structure of the circumstellar environment. And this is because a young star with a disk can in principle be observed either edge-on or face-on or an intermediate configuration. And so depending on the specific viewing geometry, we'll have different features of the star in a disk environment that cross the line of sight to the star. And so this will lead to a different type of variability. And this slide summarizes some examples of light curves that have been detected for young stars with disks in different star-forming regions over different time scales, so ranging from weeks and months out to several years. The light curves that are shown here on the left and the bottom of the slide were obtained from space with the Corot and Kepler satellites over timescales of just a few months. And this highlights the impact of variability driven by star spot modulation, which has typically a very regular periodic profile. And then the variability driven by accretion events, which is more irregular with luminosity bursts that trace individual accretion episodes. And then we have what we call deeper light curve, which is driven by inner disk dust structures that cross the line of sight to the star. So they hide part of the stellar photosphere periodically or recurrently, as the star in systems that are seen almost edge-on, or high inclinations. And if we move out to longer baselines of years, the most prominent variability features that we can observe on young stars are outbursting behaviors that are also linked to accretion processes. And you can see an example of light curve here, which spans several years, where these outbursts can develop over timescales of months or longer, or years. and they typically correspond to a much larger variability amplitude than the variability associated with shorter variability, with shorter timescales of variability. Although these previous surveys have allowed us to build a detailed view of the time domain behaviors of select young stars, all of these surveys were subject to several limitations. So, for instance, the variability surveys that were conducted from space on timescales of weeks to months usually were limited to a few star-forming regions that could be observed by the telescope along its trajectory. And also, they lacked sufficient color information that would allow us to classify the exact variability source underlying the light curve profile that we observed. And for longer-term eruptive behaviors in young stellar objects, our current knowledge is based on just a few dozens of sources that have been discovered serendipitously. And so this has limited the amount of constraints that could be provided to modelers to get a more detailed understanding of the type of physics that is governing these sources. So, for instance, outstanding questions in the field concerns the link between small-scale disk processes and large-scale eruptive behaviors. And we do not have a statistical view of how common these large-scale outbursting behaviors are over the typical premain sequence evolution of young stars. So whether this is a common stage that all young stars cross during their lifetime, or whether these are different type of objects. And indeed, very recently, there has been a new decadal survey in astronomy and astrophysics that was conducted, sponsored by several agencies, including NASA and ENSF, which led to a document that charted pathways to discovery in astronomy and astrophysics for the 2020s. And in the field of star formation, several among the questions that were found to be answered in the 2020s, we find the exact dynamics of mass accretion from large scales to small scales, and whether the mass distribution of young stars that are formed in star-forming regions is universal or not. And in order to address these questions, we need to obtain time domain measurements of stellar luminosity and their variability over a wide range of variability timescales, and for large samples of stars that cover different evolutionary stages and different regions of the parameter space in order to map this variety of behaviors. And this is where Rubin LSST can be really transformative, thanks to the unique features that are combined in the survey design. So the decade-long duration, the high spatial resolution, the coadded depth that will be reached at the end of the survey, the availability of multi-filters that will allow us to be sensitive to the inner disk processes, and the fact that these same filters will be implemented with a uniform strategy throughout the entire survey duration. So a first important thing that LSST can help us achieve is an unprecedented map of young stellar populations across the Milky Way. And this is in particular because LSST, thanks to its variation in the coadded depth, will allow us to detect the lowest mass M-type stars in all of these young star-forming regions. And this is important for two reasons. The first is that M-type stars are the most common type of stars in the galactic field, so they will provide us with a large statistical sample to classify the young populations we observe, and they are also crucial for the initial mass function. And also, the second reason is illustrated in this color diagram as shown here, that combines the color properties of stars as a function of their mass in G, R, and I filters. And what you can see here is that M-type stars show a very distinctive color sequence on this diagram, which is very different from the direction of the reddening vector on the diagram itself, which means that based on these color properties, we can readily identify M-type stars, we can estimate their extinction, and we can derive the properties of the parent population. So as part of the Rubin LSST survey strategy optimization process that has been conducted over the last few years, we have published a work led by Loredana Prisinsano, where we have considered the distribution of stars across the galactic plane and the effects of dust and crowding limits in order to derive an estimate of the number of young stars that we expect Rubin LSST will discover at the end of the survey. And this map, the resulting map is shown here. And the result was that LSST is expected to uncover an unprecedented volume of young low-mass stars, where young is less than 10 million years and low mass is down to about 0.3 solar masses, if the wide fast deep strategy for the main survey is implemented in a uniform pattern across the galactic plane. This diagram here on the right shows how this projected number of young stars that will be discovered with the LSST is distributed as a function of distance from us. And the key takeaway point from this plot is that this unprecedented number of young stars that will be discovered peaks at distances above 10 kiloparsecs, which is a volume that is so far largely unexplored because it could not be reached with previous in a systematic way with previous surveys. So this means that LSST will really open up an unprecedented discovery space that is crucial to answer all of these questions regarding star formation and the initial mass function. And this plot shown here on the left illustrates the maximum distance at which we expect to be able to detect young stellar objects, depending on their mass, on their extinction, that is shown here in the color scheme, and on their age, which is shown here by the dash of the line. And so and for these diagrams, we assumed the limiting magnitude, the phi sigma limiting magnitudes projected for the LSST survey in the wide fast deep mode. And what these diagrams indicate is that the young stellar objects that will be discovered by LSST at distances beyond 10 kiloparsecs will not only be discovered in the filter in the Redus filters, but will be identified across the entire filter range, which means that not only will be able to chart these populations, but we'll also be able to characterize them. And the other key element that LSST will provide is a uniform description of the variability behaviors for these young stellar populations that will be identified. And this is important because it will provide us with a tool to validate the populations that we detect and to distinguish the bulk of young stellar objects from field contaminants. And this concept is shown here on this diagram on the left, which was built using different light curves, so light curves obtained with Corot on different timescales, where it was shown that if we combine typical variability information, such as the typical amplitude of variability and the timescales of variability, we can distinguish the bulk of field stars from the bulk of young stellar objects. And the other key element is that if we have variability information in different filters, we can study how the variability amplitude scales with wavelength, and we can compare this with the expected emission properties of different sources of variability. So for instance, if you have a cold magnetic spot or a hot accretion shock or a dust clump within the inner disk. And so we can fit the observations with these models, and this helps us get an understanding of the physical structure of the young star and its surrounding environment, and pinpoint the origin of the observed variability, which was a missing element in previous surveys. So in order to do this, we need a homogeneous framework in order that allows us to characterize the variability timescales and variability properties of young stars across several orders of magnitudes. So from the shortest timescales of variability to the longest ones, and which can be applied to any light curve, irrespective of its shape. So both for periodic sources and for stochastic ones. And to do this, we have started using precursor data, such as Gaia and ZTF, and implementing different methods, statistical methods that are agnostic to the shape of the light curves. And in particular, the example I'm showing here implements the method of structure functions, where we start from the light curves of the object, and we obtain a plot of the average amplitude of normalized flux variability as a function of timescale, where the timescale is allowed to span the entire range covered by the light curve. So from the shorter timescale that we are considering in the light curve, which is the data cadence, out to the longest timescale of variability, which is the time series duration. And what this statistical analysis provides us with is an estimate of the leading timescale of variability, which is the timescale at which we measure the maximum amplitude of variability across the time series. And then a measurement of how this maximum variability, amplitude of variability we observe changes as a function of wavelength if we have light curves, simultaneous light curves across different filters. And this is a work that is currently in preparation, led by Sabina Ostamovich. This also produced a DP0 delegate contribution in the form of a notebook that explains this analysis and implementation not only for young stellar objects, but for any kind of variable source. So the key result of this analysis is that a uniform sampling of all the timescales of interest is critical in order to connect the different phenomena that are characteristic of young stars and their disks. And so the plot I'm showing here on the left is a diagram extracted from a recent paper by Federica Bianco, which illustrates the typical expected separation in time between two consecutive visits to the same LSST field, either irrespective of the filter that is used, so the minimum separation in any filter, which is around 3 days, or in a specific filter. And so what these estimates tell us is that the Rubin LSST main strategy, survey strategy, so the wide fast tip strategy, will allow us to naturally identify transient behaviors and dramatic flux changes in young stellar objects that occur on timescales of months or years. But this is not sufficient in order to reconstruct the shorter term variability that we need to connect the small scale to the large scale variations. And so we need complementary approaches in order to reconstruct this short-term component of the time domain. And this is the focus of another work we have published as part of the LSST survey strategy optimization process, where we have taken as a reference the light curve of a young star dominated by accretion events that was obtained with the Coral satellite. And we've considered just a segment of the light curve extending over about 1 week. And then we have explored how different survey strategies that have been considered for LSST, so different implementations of the survey simulations would allow us to fill in this variability profile. So here the plots I'm showing correspond to the wide fast tip cadence, the deep drilling field cadence, and then an ad hoc cadence that we consider to reconstruct the shorter timescales. And what this exploration told us is that neither the wide fast tip cadence nor the deep drilling field cadence would be sufficient for us to reconstruct the short-term variations of young stellar objects. And the optimal way to extend the LSST young stellar object science to the shorter timescales will be to complement the wide fast tip survey with ad hoc shorter high cadence surveys. So a macro survey extending over about 1 week with sub-hour cadence in the different filters in order to retrieve this short-term variability component. And the same strategy would also benefit multiple science areas, such as the characterization of stellar activity, eclipsing binaries, or planetary transits. And if you want to know more, please check out the poster by Alessandro Tramuto, which will be presented in the lightning talk in the next block. So to conclude, time domain surveys provide a unique window to encode the physics of young stellar objects, and homogeneous surveys of large samples of young stellar objects, so large samples of young stellar populations, are essential if you want to address long-standing questions with regards to how stellar mass is assembled and on the initial mass function in star-forming regions. LSST will be, thanks to its characteristics, will be uniquely suited to build a homogeneous and comprehensive view of young stellar objects across much of the time domain of interest if we can implement a wide fast tip cadence that is extended to the entire galactic plane, and if we can complement this with short-term higher cadence surveys of targeted young stellar object fields in order to maximize the LSST impact on the young stellar object science. And of course, once we've used the LSST as a discovery machine for young stellar populations, ground-based spectroscopic follow-up will be essential to, for instance, confirm the nature of newly discovered eruptive young stellar objects, and also to study the connection between mass accretion and mass ejection processes by considering diagnostics that would not be available to us from LSST alone. Thank you for your attention.
Thank you very much,